Good morning, everyone. I'm Shreyas V. Achari and my teammate is Shrikar M. Shetty. We are from batch A16. The title of our project is Sentiment Analysis Using Brain Signals. We are doing this under the guidance of Professor Rashmi Patil. In today's presentation, we will be covering the following topics. Coming to the project objectives, these are the objectives that to create a testbed of brain signals and also to develop a model for emotion recognition using brain signals. Our last objective is to extend the model for predicting more mental states. So, looking at the problem statement, the main objective of our project is to develop an automated model for emotion recognition using EEG signals with the help of neural networks and consumer EEG hardware. So, what's an EEG? Basically, an EEG is a machine that uses tiny metal discs, commonly known as electrodes, placed on the scalp to detect electrical activity in human brain. This activity appears as wavy lines on an EEG recording. And we all know that the brain cells communicate via electrical impulses and are active all the time, even when you are asleep. These EEG signals are basically classified based on the frequencies. Coming to delta waves range from 0.5 to 4 hertz, and theta ranges from 4 to 7 hertz. And both these brain waves, that is delta and theta brain waves, are generated during deepest meditation and deep sleep. Coming to alpha waves range from 88 to 13 hertz, and these brainwaves dominate in a calm, relaxed yet alert state. Beta brainwaves ranges from 30 to 13 hertz. These brainwaves are most commonly seen when focused and performing a cognitive task. Gamma brainwaves range from 30 to 200 hertz. These brainwaves are the fastest brainwaves and are more related to stress, fear, and panic. So coming to the setup, how signals are captured. We have made use of a Muse 2 headband which consists of 4 electrodes. On the right hand side you can see the positions of the electrodes which are to be placed on the scalp in blue. The headband will be placed on the scalp in such a way that the electrodes are on the positions. In our project we have considered two mental states, that are stressed and relaxed state. In order to record the brain waves during the stress state, we had asked a person to solve Sudoku problems. And to record the relaxed state, we asked the person to sleep or meditate for a while. This recording was conducted for approximately 14 to 15 minutes per person. Coming to the architecture, starting with the EEG signal acquisition as explained in the previous slide, after acquisition of all the signals, we'll be having the test bed that is also known as a data set. And after we have the data set, we'll be performing some kind of filtering and pre-processing on the data set with the help of few Python libraries such as NumPy and Pandas. In this process, we'll be eliminating few external attributes which are not required for our project. After filtering and pre-processing, coming to the deep learning model, here we are going to build a neural network which takes the raw EEG signals as input and predicts the mental state. That is, in our project we have considered only two, that is relaxed and stressed. Next, coming to the neural network, what a neural network looks like. So we have made use of three layers excluding the input and the output layer. That is GRU is the first layer, that is gated recurrent unit, and second layer is flattened layer, third one is dense layer. The gated recurrent unit is part of a specific neural network that intends to use connections through a sequence of nodes to perform tasks associated with memory and clustering. And this gated recurrent unit layer will be having output in multi dimensions. So to reduce the dimension, we have made use of flattened layer. So what flattened layer does? Layer just flattens the multi-dimensional input tensors into a single dimensional input. So the output of the flattened layer is given to the dense layer. So basically dense layer is a layer that is deeply connected with its preceding layers, which means the neurons of the layer are connected to every neuron of its preceding layer. So the output of the dense layer is nothing but the expected output. That is, it will be in the form of binary as of now, because we have considered only two mental states. It will be either 1 or 0, that is stress or calm. Coming to the applications, This can be used by professionals in the medical field to track mental health issues such as anxiety, depression, and stress. As you all know that in today's world, mental health is becoming a very big concern, and it can also be used in improving the gaming experiences. So let's look into the implementation part. So here you can see the Google Colab file, wherein we have started by uploading the CSV file, that is the data set, and we'll be looking at the all the attributes, including the timestamp and different brain waves. After this, we'll be eliminating the null values. So as we all know, there will be slight disturbance while collecting the data. So when the device is displaced from that particular electrode's position, that particular data will not be recorded. In such cases, null values will be added in the dataset. In order to remove the null values, we have made use of Python libraries. As you can see here, we have made use of this command, that is drop NA, and we have eliminated the null values. After eliminating, we can see all the data set, all the attributes in the data set are non-null. And we have also made use of a few visualization to just check out how the brain waves are functioning. So this is pretty much about the pre-processing part of the dataset, and then after this comes the training part. So here you can see these are the libraries which we have made use of. So initially we'll upload the dataset here, and after uploading the filtered dataset, we'll be just looking at it. So these are the attributes, and these are the different rows in which the brain waves are stored. And after that, we'll be uh, considering only that certain part of the dataset for training the model. For this, we have made use of ilog command. So after this, we have visualized the dataset. Here you can see the analog format in which the brain waves are acting. After that, we can see we have used label encoding for encoding the mental states. As we have made use of only two mental states, after encoding it will be 1 and 0. That will be in a binary format. And after that, we have split the dataset into two parts. 70% will be used for training dataset, and rest 30% will be used for testing dataset. First 70% will be used for training the model, and next 30% will be used for testing. In the next command, next block, you can see that we have made use of three layers, excluding the input and the output layer. First layer is the GRU, that is gated recurrent unit, and second one is flatten, and third one is the dense layer, you can see here. So this is how the different layers look like: input, and then that will be going into the GRU, that will be fed to the flatten, and further into the dense layer. So here we are saving the neural network in the local memory, which can be further used in other machines as well, wherein if we give any raw data as input, it will predict the mental state and give you the output. So after training, here you can see we have achieved the accuracy as 81.81 percentage, and further we'll look into the testing phase. Coming to the testing phase, and these are the libraries which we have made use of. In this part, we are going to give the test file as input. That will also be in the form of CSV. Here you can see the data set which will be feeding into the neural network in order to predict the output, that is the mental state. So here we have chose one particular row as input just to check out whether it's giving the proper output or not. So after execution of this command, here the neural network will be fed, will be uploaded, and then the gender column will be encoded. After that, here you can see we have used model.predict for predicting the mental state, and the value will be fed into the neural network, and the output, if you here you can see, is calm for this particular row. So this is how our neural network works, and coming to the conclusion, Emotion detection for EEG signals can play a very important role in identifying early signs of depression and mental illness since EEG signals are more accurate in pointing out such scenarios. It can also be used to study the impact of music or yoga on the brain. In short, in our implementation, the dataset was first pre-processed using Python libraries such as NumPys and Pandas, and then the neural network was developed, which would give the mental state as output by taking the raw brain waves as input. And we achieved an accuracy of 81.8% on the dataset that was generated by using the Muse2 EEG headband. Thank you.